Hello everybody, welcome back to our channel. In this episode we're going to be solving a Physics 7B linear transport and exponential decay practice problem. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe. It really helps promote our channel. So this is the problem that we're going to be working with. We have two identical standpipes that are connected by a thin tube at their bottoms. The standpipe on the left is 15 centimeters higher than the standpipe on the right. And then the initial water level in the left standpipe is 16 centimeters from its bottom. And then the water on the right initially is 4 centimeters from its bottom. The first thing that we have to figure out is if the resistance of the tube connecting the pipes is 100,000 joules second divided by meters to the 6, what is the initial current flowing through it? Alright, so as you can see, I have everything written down here. So there is a 15 centimeters difference between both of the standpipes, and the initial height from the bottom of the water column to the top over here is 16, and for this one is 4 centimeters. Now, the first thing that we are asked is, at this initial point in time, if the resistance is equal to 100,000, then what is the initial current flowing through it? So at this point, we are not really looking at anything over here at final. We're just looking at the initial condition, and basically we want to find, obviously at t is equal to 0, some of the water is going to start flowing this way. It's going to want to go down. So we need to find the value of the current. So for this part, we're basically just going to use our knowledge in fluid transport, and we are going to use our Bernoulli equation a couple of times. So basically we are going to do this, and I'm going to call this, let's just, call it A, and let's just call this B. And we have to use our Bernoulli equation 3 times. So the first thing that we have to do is find the pressure at point A. So what I'm going to do is I'm just going to use a Bernoulli equation from here to here. And if I start over here at the top and go to the bottom, then delta P is going to show up, and then I don't have a difference in height. I don't have a difference in area. I do have a difference in height. I'm sorry. I don't have a difference in area, and then because this is just the beginning of the experiment, I don't really have any resistance over here in the column. This resistance is just over here in the thin pipe. And also there is no pump, so this is just equal to 0. So this guy over here is just final minus initial, and I decided to go down. So this is PA minus atmospheric pressure is equal to negative rho G, and then this guy over here is this change in height, but I decided to go down, so this guy is actually negative 0.16 centimeters, yeah, so 0.16. So the pressure at A is just atmospheric pressure plus rho G 0.16. Now if I do the exact same thing, but now I go from here to here, going down, then what I'm gonna get is, I'm gonna get the exact same Bernoulli equation because I'm still just going down a water column. The only difference is that I'm going through the right water column, so now it would be pressure at B. And also now I'm gonna be using these 4 centimeters. So like this. And now the reason why I'm doing this is because now I want to go from A to B across this pipe over here. Like this. And my Bernoulli equation is basically going to be delta P. And then I do have another potential energy term because I do have an extra 15 centimeters in height, so plus rho g change in y. I don't have a change in area going from here to here, and I do have some resistance and some current, so this is equal to negative IR. Okay, so now I just need to solve for I. I have everything that I need because this guy over here is just this change in height, so this is 0.15. So let's just go ahead and solve for I. Let's see. So I is delta P plus rho G negative 0.15 actually, because I went from A to B, so I'm going down, divided by R. This delta P, I decided to go down, so this is PB minus PA plus rho G negative 0.15. And then I just need to substitute these two guys over here. These two are going to cancel out. So let me just put all of the numbers here. B minus A, these two are going to cancel out when I subtract B minus A. And then I'm basically just going to have this term minus this term over here. So this is rho G 0.04 minus A, which is rho G 0.16 plus rho G negative 0.15 divide by 800,000. So I is equal to rho, this is water, so I'm just going to say 1,000. G is 10, and then this is 0.04 minus 0.16 minus 0.15, and then divided by 800,000. So I is equal to, let's see, 1,000 times 10 times 0.04 minus 0.16 minus 0.15, divide everything by 100,000. And that would be 0.0 per second. Oh, no. No, I did from A to B, so I am going in the direction of the current. Yeah, that's why I was a little confused. Yeah, so see this negative sign over here? So I forgot this negative sign. I should have divided by negative R just to take care of this negative sign. So I forgot this. So this is minus and this is plus. Okay, that makes more sense to me. I got a little bit confused because I got a negative number, and you know, that would be fine if I had done from B to A, because that is against the direction of the current. And I just got a little bit confused because I got the opposite direction. But no, everything is fine. I just totally forgot about this negative sign, and if I had just put that negative, then everything would be positive. So that makes sense. So my final answer is 0.027 meters cubed divided by seconds. And this is why it's very important to never, you know, physics does have a lot of math, but it is actually very important to never forget that your answer should make sense. And that, you know, if you're going down and finding a delta Y, it should be negative. If you're going with the current, you should get a positive current. If I had gone from B to A, then yes, I would have expected a negative value. But that is why it is actually always, sort of important for you to see if your answer makes sense, not only mathematically, but also physics-wise, because if it doesn't make sense physics-wise, then you are probably missing some sign, somewhere. Alright, so let's see. So this is part A. So now part B is the actual exponential decay question, which is plot the height of the water in the tubes as a function of time. Clearly label initial and final values for the height of the water on the left and on the right. Measure the height starting from the bottom of the respective standpipe. Okay. So what's going to happen here is that, because there is a height difference and both on the water columns and also in terms of the column height, what's going to happen is that some water over here is going to go down at this rate precisely. And then our final state is going to be some state in which the water is leveled up. So something like this. So that delta P is equal to 0. But because these two are not leveled up and we're measuring our height differences from the bottom of the water column to the top, even though physically these two are level with respect to the earth, like with respect to ground level, they are not going to be showing the same amount of tick marks like over here on their water columns, right? So we basically need to figure out what the initial condition, well, no, we do have the initial conditions. We just need to find the final, and then we just need to make some graphs. So I did prepare some graphs. So I have this over here. So now we do need to figure out what the final conditions are going to be. I do know that the left water column starts at 16 over here. And I do know that the water column on the right starts at 4. That means that the total amount of water in tick marks is equal to 20. Because you have 16 tick marks over here, 4 tick marks over here, and because no water is actually leaving the system, and both of these guys have the exact same cross-sectional area, what this means is that if this water column loses a tick mark, then this water column gains 1 tick mark. So in a sense, you're gonna have a conservation of tick marks, if that makes sense. Because if you lose 1, then you gain 1. If you lose 2, then you gain 2. And you do need to have that conservation. So let's see. So let's just try to put that on an equation. And the equation would basically be that the height on the left plus the height to the right, they always need to add up to 16 plus 4 to 20 tick marks, or 20 centimeters. So we have 20 centimeters in total. Now another thing that we can figure out from this, because at this point I have the initials, so now what I want is the final values. So the final values are gonna happen, let's see, so this is the final for left. This is the final for right, and then this difference over here is 15 centimeters. So if I want to write this on equations, then I would say that HL plus 15 centimeters has to be equal to HR. And you can see it over here. You can see it that HR is equal to HL plus this 15 centimeters at this equilibrium point. So now we can pretty much use these two equations to find our final values. So let's see. So what I'm gonna do is I'm gonna take this guy and I'm going to substitute this over here. So so this will be HL plus HR, but HR is also this. So this is HL plus 15, and this is equal to 20, So 2HL is equal to 5. So the final value for the left one is 2.5 centimeters. And now from this, we can just take this number, put it back over here, and this means that 2.5 centimeters plus h right is equal to 20. So the final value for this water column is 17.5 centimeters. Oh, I just have 17. Okay, I'm just gonna go over that. So these are my final values, 2.5 and 17.5. So this guy over here, the left one, starts at 16 and ends at 2.5. So let's just go ahead and ends at 2.5. So the final value for this guy is over here. And then this other one, the one on the right, starts at 4 and it's gonna go all the way up to 17.5, which, you know, I'm just gonna have to go a little bit upwards of this, but this is, you know, 17.5. So these are the final values. So now basically all I have to do is just make some sort of exponential function over here. So let's see, if I want to be somewhat accurate, I can do alright, so I'm gonna do my best over here, but at this point, there we go. So something like this, and then something like this. There we go. So start at 4, end at 17.5, start at 16, end at 2, and this is my final answer for part B. So now sketch in where you would find a half-life on your graph. Sketch in where you would find a time constant on your graph. You do not have to label any numbers. Okay, so my half-life would basically be, you know, where the half value is. So for both cases, it would be over here. No, it is not where they meet because they have different final values. So I do need to figure out where that is. So the half value for the orange one is the middle point between 16 and 2.5. So 9.25. So somewhere around here. And then the middle point between 4 and 17.5. 10.75. So it would need to happen at the exact same time, but obviously I'm hand drawing this, so I'm not gonna get hello. I'm not gonna get an exact result for both of them if I'm just handwriting, especially on a graph this big. But this is where the half-life would be. And then the time constant is always, instead of being half of the value, is all of the value, it's 1 over e of the decay, so that your time constant is always going to be, can you maybe move a little bit? Thank you. So your time constant is always going to be to the right of your half-life. Can you please not do that? Okay, come on here. So it's always going to be to the right, and also it's going to be 1 over e of the decay. So it should just be you know, somewhere around here. You don't need to be super specific, but it's just where your time has decreased by 1 over e. So tau is a decrease by e, and then the half-life is a decrease in half. Now, the only thing that matters over here, obviously you don't have specific time values, and also which makes it pretty much impossible to just figure out like how far these two should be. Also, you don't have an x-axis that is that has like actual numbers here, so you could have like maybe drawn them more separately. So just as this guy was to the right of this guy, then personally, then I would think that's okay. And the reason why this guy should always be to the right of this guy is because of the relationship that the half-life is natural log of 2 times tau, which means that, you know, natural log of 2 is 0.69 times tau. So this guy is always going to be smaller than this guy. So long as this relationship holds, then, you know, there is a lot of there are a lot of options for how you, can you please, thank you, there are a lot of options as to how you're gonna finish this problem. So anyways, I hope that this video was useful to you. As usual, if you have any questions, please make sure to leave them on the comments. We do read them, and if this was helpful to you, please make sure to leave a like so that YouTube starts recommending our videos. And I will see you in our next